So let's look at the configuration. We have a triangle ABC. M is the midpoint of BC. P lies on the line AM, and P is positioned so that the distances AB and PC are equal. We're also given an equality of angles as marked in the diagram. This angle is equal to that angle. We're asked to prove that angle CPB is a right angle, and it certainly looks like one. I've marked on the equal lengths as red segments, but it's hard to know how to begin. We've got lots of triangles in the diagram, but none of them seem to be similar, the usual way of getting stuck into a geometric problem. So we need an idea, and here it is. Reflect P in the point M, so it comes down here to the point Q. What's the reason for doing that? Well, in a parallelogram, the diagonals bisect each other. But there's a converse to that. If you've got a quadrilateral like PBQC with diagonals bisecting each other, then it has to be a parallelogram. In fact, it's a rectangle, but we don't know that yet. It's certainly a parallelogram. Well, that tells us things. Parallelograms have opposite sides of equal length. So this red length here will be equal to this red length BQ. But now we have two red lengths next to each other. So we have an isosceles triangle. And base angles of isosceles triangles are equal. So this angle marked with a blue spot, we can install it down here as well. They're equal angles. Now, another feature of sides of a parallelogram, opposite sides of a parallelogram, is that they are parallel. We have here a transversal to these two parallel lines. And so what some people call Z angles, other people call alternating angles, applies. And this blue angle here recurs as that blue angle up there. But now the triangle MCP has got two angles which are equal to each other. So it's isosceles. The sides are equal as well. So MC equals MP, but we knew that MC was equal to MB. So you can form a circle with center M, which passes through C, and it will pass through P and B. In turn, that will make the angle CPB an angle in a semicircle. And so it will be a right angle, and so we'll be done. So supposing you didn't have that idea, how can we do this problem without having this inspiration to construct a parallelogram? Well, you can use some trigonometry. We can use the sine rule. This is a way of doing the problem by trigonometry. Look at these two angles here. The angles on a straight line, so they add up to 180 degrees. The posh way of saying that is that they are supplementary angles. The important thing about sines and supplementary angles is that the sines of the two angles are equal. And we can use that as a bridge between the sine rule in triangle MAB and the sine rule in triangle MCP. So I've written the thing out here. The first equation is the sine rule in the triangle MAB. The last equation is the sine rule in triangle PMC. And that leaves us with this equal sign in the middle. But we're given that AB and PC were of equal length. That was in the problem statement. We also know that because these two angles are supplementary, they add to 180, their sines are equal. So the middle equation is justified. Now, I'm not interested in the stuff in the middle. Just look at the outsides. This angle here is marked with a blue spot. This angle here is marked with a blue spot. So they're equal angles. That tells us that the numerators, the length BM and the length PM, must be equal. So BM and PM are equal. But we know that BM equals CM, so we can play the same trick as before and draw a semicircle with centre M that passes through C, and it will go round through P and B. And then you can finish by using angle in a semicircle is a right angle.